Welcome, everyone. Today we begin our journey into the fascinating world of quantum optics by exploring one of its fundamental components, beam splitters. Beam splitters are optical devices that play a crucial role in various quantum optics experiments and applications by dividing incoming light beams into two separate paths. Let's delve into the mathematical model of a beam splitter. A typical beam splitter takes two input light beams, which we denote as A hat1 and A hat2, and produces two output light beams, A hat1' and A hat2'. The relationship between these input and output beams is captured by a 2x2 matrix, denoted as B, effectively mapping the transformation of the beams. The unitarity of the matrix B is fundamental for ensuring energy conservation within the system. This means that the total photon number across the input and output must remain constant. Mathematically, this is expressed through conditions: the sum of the squares of the elements in the first column and the sum of the squares of the elements in the second column of matrix B both equal 1, and the product of corresponding elements across the columns sums to 0. To describe the beam splitter matrix B in a more granular way, we use phase factors and rotation parameters. Matrix B can be represented as a rotation by angle theta, accompanied by phase shifts phi, psi, and lambda. This is explicitly shown by the matrix, consisting of cosine of theta over 2 and sine of theta over 2 arranged in a rotational configuration. This structure facilitates the transformation of the input beams into their respective outputs. Turning to the practical aspects of a beam splitter's operation, we define the transmissivity, denoted as T, and reflectivity, R, in terms of the beam splitter's angle, theta. The transmissivity T is the square of the cosine of theta over 2, and the reflectivity R is the square of the sine of theta over 2, ensuring that their sum equals 1, in accordance with the principle of energy conservation. The beam splitter matrix, based on the experimental measurements of T and R, is formed with square roots of these values, providing the coefficients for matrix B as follows: square root of T and negative square root of R on the off diagonals, which ensures the preservation of total photon number and respects the unitarity condition. As we transition from the Heisenberg picture to the Schrödinger picture, we enhance our description of state transformations using operators L0 through L3. These operators account for various adjustments in phase and amplitude and the balance of photon numbers between paths, encapsulating the complex dynamics within the beam splitter. Using these operators, the operation of the beam splitter can be mathematically modeled as a sequence of exponential transformations involving the operators with respect to the phase shifts phi, psi, lambda, and the rotation theta. This sequence reflects the actual physical transformation occurring within the beam splitter as dictated by the experimental setup. In conclusion, beam splitters are not only pivotal for directing light in quantum optics, but their operation also showcases a rich interplay of mathematical transformations that preserve the inherent quantum mechanical properties of light. Understanding these principles allows us to better design and interpret experiments in the realm of quantum optics.